So we're gonna just introduce the paper and give the certificates and then the. One more minute. Okay. Good morning, everyone. Thank you for waking up for this last day of chess already. So this is a special session because it's about the best paper of the conference. So let me tell you a few words on how we identified this best paper. So for this edition with Thomas, we decided to add a field in the reviews where the PC members were had to decide whether each paper they reviewed was a potential candidate for the best paper award. So they did, and based on this field and on the novelty scores, like the impact of the contributions, we identified 14 papers in the 4 issues, and we submitted them to a vote by the PC members. So at the end of this vote, without more suspense, the winner is Miracle, Micro Architectural Leakage Evaluation by Dan Page, Ben Marshall, and James Webb. Please applaud them. Thank you. So please come, all of you. You will get your certificates in the picture. Okay, so only 2 of you. You can, yeah. So in a nutshell, the authors, they designed an infrastructure to identify hidden microarchitectural features in modern coprocessors based on power consumption, but they'll tell you more about it in a second. Congrats to all of them.
Does not matter. Okay, let's look at those. Okay. Yeah. Okay. Good morning. Can you all hear me? Yeah, thank you, people at the back. So yeah, congratulations on making it all here. I'm going to do my best after the fun last night. So first of all, thank you to the program committee, to the reviewers for awarding us best paper. This is a wonderful surprise and quite unexpected. And also a particular thank you to our reviewers. This is a 40-page paper. It was not easy to write. I cannot imagine what it was like to review. So thank you for the efforts of the reviewers. It took about 2 years of work to get this to the point where we could try and publish it, and then another sort of almost year trying to get it published as well. So it's really nice to be able to finally talk to you about it and share it in a venue like Chess. So as introduced, this paper is called Miracle, referring to the fact that it's a miracle we got it published, about microarchitectural leakage. So this is looking at How does the microarchitecture of a CPU impact the power leakage that you can observe in very basic sequences of instructions? So I'll give you a little bit of an outline to kind of the context that's really important here. I'm not going to try and tell you about all the results we found. I'll just try and give you a bit of a taste. I think the context is actually more important, so you can go and read the paper and understand it properly. I'll try and give you exactly what we set out to ask and then what we actually did, because as is so often the case in research, those two things weren't exactly the same by the time we actually finished it. Tell you a little bit about the selected results and what we think should happen now in terms of how we do this research based on what we've discovered. And also I think particularly important for a paper like this is where I think, speaking only for myself and not my co-authors, where we could have done better in this paper, and maybe this gives you some ideas for how to extend our work. And then what next? And hopefully by that point, you'll have lots and lots of questions. So, background. We all want fast, cheap, secure, everything. And this is impossible because we build our computing systems on abstractions. And these are great for managing their complexity. You start at the top, you write some C code, and you can compile that C code and you can run it just about anywhere. That's great because it will be functionally correct. And this is because we rely on instruction set architectures by ARM, Intel, RISC-V, and they provide this contract, this guarantee of functional compatibility across hundreds of different kinds of device. And that's wonderful, but it's an abstraction. So unless that abstraction captures everything you need to do to reason about the requirements of your functionality, it's not going to go all the way. And for security, we know that this is a massive problem because the moment you turn up with a stopwatch or a power probe, you can completely destroy these beautiful abstractions because they leak. They are leaky abstractions. They let you expose information about the underlying implementation of the device. So for timing, this is actually built into the architecture. It is an architectural flaw that you know how long something took. And obviously, I don't need to tell you all about the sort of extensive literature around timing attacks and cryptography. You're probably all very familiar. But you've also got power consumption, right? You've got power consumption coming from the data you're computing on, and this is affected by how the data is computed on. How does it move through the system? Which registers does it touch? Which registers get updated in the meantime? All of this. And this is very hard to capture in a model. And if your model doesn't capture all of this information, it's very hard to sort of reason about the security. So that's why I'm always very impressed when people come up with formal notions of this security. It's just a really, really difficult thing to capture. So what we wanted to do, the problem we wanted to try and solve was, how do we repeatedly and easily build an understanding for a particular device and how it behaves under sort of power leakage circumstances? So just looking at really basic sequences of instructions, how do they differ? Do all devices behave the same? Do they not? What is the difference between those devices? And where are my notes? Yeah, we kind of wanted to do a little bit of a reverse engineering exercise, basically, because there's been lots of papers in the past that focus on, a particular device or a particular cipher on a particular device. And we wanted to back up a little bit. This is not an attack paper. This is not a countermeasure paper. This is just doing fundamental research into how do CPUs behave if you care about power consumption and the leakage it might lead to. Oh, good. I should have really moved on a slide. So yeah, we wanted to understand, what does the ISA expose to you? What tools does the ISA give you to understand the implementation? And we did this because we had a lot of guidance from past papers that sort of mentioned, during building this leakage-resistant AES, we found some registers that ruined our results, and we had to do this little change. And there's dozens of papers that kind of mention this, and we kind of refer to this as the folklore of the literature. Every postdoc, every PhD who's tried to write some leakage implementation stuff has kind of come across these effects, but no one's really written them all down in one place and tried to repeat them. That was what we tried to do. We didn't really know why no one had done it before until about 6 months in, and we realized how hard it was. And we wanted to, see, okay, we kind of know something about designing CPUs. There's only so many sensible ways of designing a microcontroller. So let's try and use our knowledge of that to find new problems that other people can go out and solve. And we wanted all of this to be reusable. We wanted to make sure that we could create a suite of programs that you could all take out and run on a new device and kind of characterize it from the point of view of, okay, these instruction sequences are going to leak, so I need to do something about that in my leakage resilient program or my tool for capturing leakage and modeling it. We wanted to also, assess, do different devices leak differently? Spoiler, yes, they do, and we'll see why in a minute. And we also wanted to try and explain all of this. It's really hard to create a coherent way of explaining all of these results. And a paper turned out to be a really horrible way to try and do this, because sometimes scientific publishing doesn't let you explain all of the things that you really want to explain in a paper. So I'll talk a little bit about how we got around that as well. So the kind of papers that led us to try and investigate this is a selection of them that you all should definitely go out and read, because they're great. There are many more listed in the paper. But I think some of the standout ones for me are the Mind the Gap paper. They were kind of the first ones I'm aware of that did a real, I don't know, deep dive into some of the effects that we investigate here. They sort of looked at load after load leakage, and how if you have two load instructions separated by a bunch of ALU instructions, oh, actually the two load values still leak. Why is that? It's quite interesting. And it was a great starting point for us to try and replicate their experiments across a bunch of other devices. The other one I want to kind of call out is the one on the bottom right there, on the effect of microarchitecture leakage. That's probably the closest other paper out there in terms of what we tried to do. They looked at 4 devices and a bunch of different experiments. And having read the paper, I think it's great because our results kind of reinforce one another. So it's quite a nice validation. So the point of Miracle was to sort of take all of these works that look at a particular device or a particular cipher or a particular effect, bring them all together and under some sort of coherent framework. But first, we needed to describe the problem. Why is my implementation broken? And we all know what the literature is like in terms of terminology. So we decided, okay, we're going to take all of these different terminologies that everyone else uses and introduce a new coherent one just for our paper. We hope it's somewhat useful, but it did mean that when we found different effects, we finally had a consistent vocabulary for describing them. So for example, it let us pick out the difference between, there's leakage from combinatorial logic. That can be glitching, or it can be from non-glitching, because sometimes combinatorial logic just changes. That's by design, whereas glitching is not. And it let us tease out these effects. It was also, as we sort of did more and more experiments, we found out that you have to differentiate between leakage that occurs within an instruction or because of interactions with other instructions. And you also had to work out, is this leakage because of a feature of the architecture? Is this like an ARM thumb instruction that forces you to overwrite a destination with a source? I would call that a source of architectural leakage because it's built into the ISA, thanks ARM. Or is it something that's happening because of a choice someone made in implementing that? So there's microarchitectural leakage, and it's really microarchitectural power leakage, or MPL as the paper refers to it, that we really wanted to dig into. So this is sort of the map of how we tried to describe each of the effects we found. You can disagree with it if you like, but we found it quite useful. Which devices did we look at? We looked at 16 devices in total, or rather we actually published results on 16 devices. There were others, but getting embedded tool chains to work is a really cursed process, so some of them didn't make it. But we had 3 broad evaluation platforms. We had the Scale platform, which was developed by Dan at the University of Bristol as a teaching aid. We had the Chip Whisperer platform, basically the Chip Whisperer UFO board. We just went and bought all of the microcontrollers that you can plug into it. Pretty easy. And if Colin is in the room, thank you. We could not have done this without you. And then we also used the Sasibo G3 platform to look at FPGA-based microcontrollers. So those were the microblaze things that Xilinx will sell you. And also we looked at the Pico RV32. And this is important for a reason I'll get to. We had 4 different device vendors. Again, this is important. We wanted to try and answer the question, does an ARM Cortex-M3 leak differently when it's implemented by NXP versus when it's implemented by ST Microelectronics? Interesting. And then 6 different sort of models of CPU. You've got your regular ARM Cortex-M somethings that we all know and love from the leakage literature. You've also got the microblaze chip that's built into the, well, it's a soft core built into the Xilinx FPGAs, and then Pico RV32 as well, which is an open source RISC-V chip, or design rather. We had 5 different pipeline architectures. Again, really important. How does my leakage resistant code behave differently on different pipeline architectures? How do the forwarding paths affect that? Really, really important to know. And then we've also got 6 different instruction set architectures. So that's the functional guarantee versus the actual implementation that you're trying to match. Yeah, so just want to ram home. This is a lot of devices to try and manage. It was pretty horrible. But I think platforms like Chip Whisperer are amazing for enabling this kind of research. So can't say that enough. In terms of the actual micro benchmarks that we tried to construct, there's a little sample of them there, but basically they are tiny little programs that are re-implementing very, very common sequences of instructions. They're not S-boxes, they're not masked gadgets, not anything like that. It's just sequences of very, very common instructions that you get across all microarchitectures. So this example set here, these are the ones we tried to work out, or that we used to try and work out, do consecutive load and store instructions leak, even if you put an ALU style instruction within them? So you've got load then store then load, store then store, all of these. And we always used each benchmark to drive a hypothesis. So we had a hypothesis, does load after load leak? That's a hypothesis. Then we go and implement that test for all of the architectures that we're looking at. And this was the same for everyone. So this is very hypothesis-driven work. In terms of some results for this, so we found that different CPUs behave completely differently on these very, very, very fundamental sequences of instructions. So each row here represents a particular CPU, each column represents a particular experiment. So you see that load after load, that's a very common effect. And I think lots of people have found that in their work. But when we start looking at load then store or store then load, we find that actually different CPUs behave quite differently. In the middle there, the ARM S2 and S3, those are both ARM M3 cores implemented by ST Microelectronics. So on the same CPU core, on the same architecture, implemented by the same company on two different devices, you've got completely different leakage behavior for load and store instructions, which if you're trying to either create a robust implementation or an optimized implementation that is portable, that's just a nightmare, right? You've got such different behavior for something so fundamental. And this was quite surprising to us, but we're also very happy to find it. So another thing that we found, we wanted to look at speculative leakage. So put aside what you know about speculative leakage from the world of Spectre. This is kind of related if you squint a little bit, but it's also quite different. Basically, pipeline CPUs run ahead. They fetch more instructions than they execute. This is just the nature of pipelines. Now, what we wanted to know is there an instruction that is architecturally speaking, not executed? So if you're running an architectural leakage model and you're just fetching instructions one at a time, you won't see this effect. This is quite important when I talk about something later, but the instruction is still fetched. It still does something in the microarchitecture, even if the result is thrown away. Does it leak? Yes, it does. So you can see in this little example here, after the done label, we've just got a bunch of XOR instructions. And all we did was go, is there Hamming distance between RA and RC, RB and RD, and the power set of those? And lo, for some CPUs there is, for some CPUs there is not. Why they differ, I'm not sure. I'd probably need to look at their source code to know exactly why this is happening. And ARM, for some reason, didn't want to let us look at the source code of all their CPUs. But that's just one experiment we did. You can see for all these other experiments, looking at different kinds of jump and branch instruction, even then the results are quite different between CPUs. To our knowledge, no one's really looked at this. No one's looked at microarchitectural power leakage for instructions that were never executed, which is kind of frightening to think that something that you didn't do can still cause leakage. And this is really important because when people build leakage models, they usually assume that only executed instructions leak. And an executed instruction is one that the programmer can see the result for. This implies that even if you didn't execute the instruction, there's still some leakage. Can you exploit it? I have no idea. But that's not what we were trying to look at here. We were just trying to look at if you wanted to build a complete leakage model, do you need to include this? I think you probably do. So that was two of our sort of case studies. There are 5 case studies, all looking at different kinds of categories of effects. The other ones looked at ALU instructions and how the operands and the results intermixed in the pipeline registers. We've also got quite a few that look at the memory hierarchy. So again, a lot of works tend to look at the CPU only. We kind of tried to expand our scope to the uncore, the memory interconnect. And again, we found quite different behavior in terms of how memory instructions worked and interacted in the core. So if you end up with weird scenarios where if you're loading different memory locations to different architectural state from different aligned bytes, those bytes can still interact for some weird reason. As someone who's designed CPUs, I can sort of look at that and go, oh, I can see how someone would have written it that way. But by the time you're sort of building a CPU for leakage resilience, you're like, why on earth does that happen? It's really weird. So there's other things to look at if this has piqued your interest. In terms of sharing all of this, we couldn't put all this in a paper, it just wouldn't work. So all of the experiments, all of the code and the tool chains and everything for getting it up and running on all of these chip whisperer devices, it's all on GitHub. I apologize to all of the postdocs and PhDs who get pointed at this. It is my code. Embedded code is pretty cursed. There's no easy way to really structure all of that code for lots of different devices, but we did our best. Feedback accepted, as well as pull requests. But it's all there, and I think that's the really important thing. We want these benchmarks to be repeatable and reusable across other devices. Otherwise, this work is kind of pointless, right? If we can't repeat side channel experiments, it's not science. We also built a browser-based interface for actually looking at all of our results online. Again, we couldn't put any graphs in the paper. There just wasn't space. So we shoved them all online, and you can pick 2 CPUs, compare the results for them. So this particular graph has the STM32 F3 and F4 looking at load after load. One of them shows leakage, one of them doesn't. Fun stuff. The fun bit. So I'm really happy with what we achieved, but I do think there are areas that we could have improved and done better in. The first was there's actually quite a lot of papers that talk about these sorts of effects, and we wanted to sort of systematize them and bring them all together, but we ran out of space. The reviewer said, no, do this in another paper. We want more information on how you did your experiments. So that got cut. But I think if people want to write a big SOC paper on the sort of the lineage of all this work, I think there's a really good opportunity there. We also quickly found that when you're comparing lots of different devices, they all have completely different noise floors and noise signatures. So having a consistent quantitative way of saying this is leakage, this is not, would be really good. Unfortunately for us, it became a very manual process. We had to sort of look, is there a correlation peak or not manually? And that was quite difficult. So that's, again, another thing we could have done better. And we also kind of went for breadth over depth. We wanted to show people mainly that there is such difference between different CPUs. This is worth investigating more for particular experiments. So we could have gone in deep on any one of these experiments, but again, we just wanted to show breadth. We also really wanted to include an x86 microcontroller, but man, just don't try. Those things are horrible. Yeah, with no apology to Intel. Like, get your tool chains together, man. So conclusions, like what have we learned from this? So one, in the literature, we need to be a little more specific about naming our devices. If you claim leakage resilience on an ARM M3 microcontroller, this means nothing because different ARM M3s leak differently. So you need to say the exact device that you tested it on, and that is the limit of your claim for leakage resilience. If you want to claim any broader result, you need to test on more than one device. And that's more work, but I think it's worthwhile because, hey, the holy grail of sort of leakage resilient software is something that's portable that we only need to write about once and forget. And we can't do that unless we know which devices we've tested it on. So that's one really important thing. Moving on from that, again, if you're actually implementing a master implementation of something, I think we need to start using more than one device to show that it's leakage resilient. We didn't look to see which devices people actually used for, first order secure AES, but I wonder if it's on the slightly more leaky M3 or the slightly easier to write for M3. We found exactly the same thing on Cortex M4 devices as well, different M4s. Well, no, the same M4 implemented by the same manufacturer on different devices, it leaked differently. So which ones should we use for evaluation? I kind of leave that to you. But what I do think when people like NIST are saying, okay, this is going to be our standard evaluation platform for the LWC competition or the PQC competition, they kind of need more than one, right? If we all develop on just one device, we're going to end up with quite skewed results. Kind of simple observation, but it might make me unpopular for the amount of work it generates. And then if you're building leakage models, again, you kind of need to do the same, or you need to say, we have built a leakage model for this device. Which makes me think, okay, building leakage models for a particular device isn't actually what we want to focus on as a community. What we should be doing is generating a methodology, a flow to say, here's my device, here's some tooling, and I'm going to push a button and it's going to generate a leakage model for this device. And I think a nice way of validating those models is to run the kinds of experiments that we've shared as part of the Miracle study. They kind of become they become unit tests for your models, because they're modeling the very low-level behavior of the CPUs. I think this is quite a nice thing to do. And I think papers like Coco or I couldn't find a short name for this paper, but masking in fine-grained leakage models, these are great examples of that kind of direction. They're building models using sort of formal basis, and I think sort of the empirical side that Miracle tries to do, there's a really nice tie in here. So what next? Well, there's always more devices. Everyone's bringing out microcontrollers all the time. We can always add to this really easily. And there's always more microarchitectural effects. Like I say, we went for breadth, not depth. There's more out there, folks. The truth is out there. This was not an attack paper or a countermeasure paper. Can you exploit these? I don't know. And you might say, well, if I can't exploit these, why do I care? Well, you know, I work in industry now, so I care because it means I can fail a leakage evaluation when I'm trying to get my thing certified. That's why I care. I don't necessarily care that you can't recover the key. It's just got to pass the leakage evaluation. So you kind of got to broaden your scope about what you care about now. Which types of leakage are more or less dangerous? Is it sequential? Is it combinatorial? Is it architectural, microarchitectural? Which one's easier to exploit? I don't know. And then how do we look at not just the CPU, but like I said, we were starting to look at the wider system because it all has an effect. And the bigger picture, this is kind of my challenge to the community. So if you work in SAT solving and you work in sort of that area of academia, they have this language called SM2 or SMT2 that is like a common interface to all academic SAT solvers, so they can all run competitions together. I think we should create a standard way of describing what do instructions do to microarchitectures, and then vendors of CPUs can say, hey, this is what each instruction does. Go away and build a leakage model for the CPU. And it becomes really easy to just focus on the modeling rather than sort of actually reverse engineering, which is what we spent all our time doing. So yeah, thank you for listening. It's been a pleasure to present this. I can't emphasize enough, this took so long. It took longer than the average postdoc contract to actually get this work out. So I think there's probably something to be said there about being able to do fundamental engineering research and present it at a venue like Chairs is really, really valuable. And anything that enables that is really good. So thank you for listening. Congratulations for making it all the way through after the banquet. I really hope you've got some questions.
Thank you, Ben. Is there any question in the audience?
Ooh, interesting. So just to make sure I've understood the question, you wanted to make sure that given you're operating on a 32-bit word, do different bits leak different amounts? We could absolutely have tested that. Yes, it's probably in our data set somewhere, but we didn't pull out the results. Yeah, but that would be a really interesting way to look for different implementations of the same CPU implementing differently, because that kind of does bit 0 leak more than bit 2. That's very much more dependent on the synthesis and the place and route of each device. So yeah, that would be a really interesting follow-up.
So,
oh,
sorry.
So the life made our experiments much easier here in that none of these platforms have CPU caches. They're all microcontroller targets, so CPU caches aren't a thing. Not in these platforms anyway, they do exist, but not here. If you wanted to try and write leakage resilient code for a cache, man, that's just a next level world of pain, because you don't know where your stored data is going to end up in the cache. You're going to evict a different cache. Like, oh, it's a mess. Definitely something that you could try and model formally, because you can reverse engineer the eviction behavior of the cache, especially if you know its replacement policy. So yeah, definitely a cool thing to look at. The only kind of caches that these platforms really have are the flash caches. We didn't look at those. We deliberately tried to keep everything executing in SRAM because it made our analysis and life a little bit easier. But yeah, definitely, you should write a paper on that.
Because the ersten Weg der Aktienstrafen ist für Short-Like oder für Solutions. Which we don't know, although you consider the one effect possible with the CPU and economic happens, there is the business enough, the point enough to do this integration.
So we definitely saw different pipeline effects, different pipeline lengths affecting our experiments completely differently, as you might expect. One of the interesting case studies to look at there is the MicroBlaze core. So it's the same fundamental microarchitecture, but Xilinx let you parameterize it between 3, 5, and 9 pipeline stages deep. So it's a really cool target to investigate this in. The way we tried to compensate for this difference in pipeline length for our experiments was to basically pad with an inert instruction. We didn't use NOP. You can't use NOP for this kind of thing because it has no guaranteed architectural effect, but you can use another inert instruction like ANDing something with itself, just making sure that register doesn't do anything. So yeah, we pad the prelude and the exit lude of the micro benchmarks to make sure that it's just that going through the pipeline sequentially and nothing else. But yeah, you're right. That's exactly the kind of nightmare that I had to spend a month trying to work out. How do I do this across a bunch of different devices? Hello. We did not, but I would be fascinated to know whether our revisions differed. Yeah. As far as I know, the main difference I could observe, because we did try and work this out, we looked at the actual device data sheets for the cores that were leaking so differently. For the M3 case, I think the one that leaked less was marketed for sort of medical applications, and they said, oh, it's very low noise, it doesn't do very much. Ah, interesting, okay. And then the one that was leaking somewhat more, forgive my terminology, was sort of high performance, this thing goes fast. I'm not sure why exactly that makes such a difference. It could just be that someone forgot a register enable, and it's behavior that you don't care about during the verification stage. So yeah, I think the thing we could see was that the way the device was marketed seemed to correlate with the behavior, but I'd love to know if it's a later generation M3. I think that would be a really cool thing to know. All right. Oh, I mean,
please repeat the question.
Engineering challenges. Yeah, I mean, if you search the Git commit history for expletives, that would probably be a good way to work out what the problems were. I think the first problem we faced was, okay, how do we just get all our programs to compile for all of these different devices? And you know, I learned an awful lot more about make files than I really want to know to do that. That was one thing. The other is, how do you keep a consistent measurement setup across different devices? This is not something I'm sure we solved perfectly, but it was good enough to be confident in our results. The other was just, how do you collect this volume of data and then analyze it sensibly? Like I ended up talking to social scientists about how do you compare different data sets like this. And that was kind of why we built this web-based interface, to try and have a tool that we could easily compare different devices with. There were numerous others, but those are the ones that I still wake up from nightmares about.
Okay, one question. So yeah, go ahead.
So defining an interface for these things. So there's a more piece of work on networks and networks.
I'm sorry, I couldn't quite understand the question. You're saying how do RTL simulations fit into this? Okay, so RTL simulations definitely have their place if you've got access to the RTL. So if you can do this, if you're a vendor, ARM, NXP, ST, if you're here, if you want to publish this information, it would make our lives much easier. The reason an RTL simulation is so important is because the reason these effects can manifest or not can literally be down to just one lazy engineer including an AND gate on whether or not the register update enable is there or not. And you can't really find that out as the root cause unless you've got the RTL and you can see it toggle in the waveforms. So I think as a way of working out what's going on, yeah, use RTL simulations, man. They're really helpful.
So we also have one online question about the speculative execution regarding leakage from non-executed instructions. Is there a difference in the leakage compared to the same instructions being executed?
Ooh, that's a good one. No, not really, because when you say difference, you do see different halves of the instruction leak. So typically a non-executed instruction will only leak the part of it that reads its operands, because the result is going to be thrown away. So the leakage is different in that respect. In terms of the magnitude of the leakage, still there, still detectable. There was no obvious like weakness in the correlation because it was executed or not. So yeah, and the reason for that is fundamentally it's the same CMOS logic toggling in exactly the same way, regardless of whether the instruction is thrown away halfway or not. So yeah, that made sense to me as someone who's had to build a CPU pipeline. Yeah.
Okay, thank you. Thank you, Ben. We are running out of time. So next question in the coffee break. Thank you. Thank you, Ben, again. So we have a quick track switch break for those of you who want to go in the other room.
Oh, good morning. Are you the first presenter?
No, I'm in the session afterwards, but I have an issue with the slides that apparently were not loaded, although I sent an email.
I can check.
So maybe if you can check, otherwise I have to speak with me.
Yes. Can you tell me which session are you?
It's the next one, so this one that starts now, the other the
Side
one,
channel attack. Which
Yes. second.
you're the second, so this should be PDF.
Okay, so you had them. Great.
Yeah, 22 slides. Okay.
Yeah, that's fine.
Okay,
No,
great.
well, maybe I can. You will quickly go through it. So, yeah, that's
Yeah.
fine. It's fine.
Okay,
Take me
no problem.
well, it's not the last version, but it's fine. It's quickly happen.
Yeah. If which microphone would you like to use? Maybe this one, and that one. Maybe this one. Okay, yeah. But for now, I'm sorry because we had some technical issues, so you will have to change slides like this. Is it okay?
Yeah, no problem.
Okay.
Okay.
we usually have a pointer, but I cannot find the USB.
Ah,
connected to it.
ah,
I'm trying to
okay.
find it maybe, but
Yeah, sure. Is there a laser for this laser pointer for this?
yeah, it should be if you put
Okay.
it's not on. No, wait. Okay, the USB was yes.
Ah, okay.
It goes off. Yeah, great. it
Okay,
works.
thank you.
There is a later point,
Ah, okay.
so everything works.
Yeah, okay.
I think we're waiting for session chair to introduce you, but I don't know.
Yeah. I know she's just here.
Okay.
Yeah.
I'm going to set up the timer here for you.
Okay,
You have 17 minutes.
okay.
The timer will be in green while you reply when it's okay. Once it goes to red, it means it's time for questions and you should end up your presentation. Okay.
Okay.
Um,
I'll maybe go a little bit over time, but okay, I'll try to see.
yes, I mean the session chair will.
Yeah. Okay. Hi.
Recording or you're handling that, right?
Yes.
Okay, perfect.
So you just turn it off when you finish. Yeah.
So how do I turn it on? Sorry. Hi, Prasanna. So we are waiting 2 minutes. Coming.
So is it a hard stop at 17 minutes or can I go 17?
I think it's okay, but yeah,
Yeah.
no more than 1 minute more. I'll be
Sure.
taking the time.
Sure. Sure.
Good evening, everyone. So welcome to the second session on attacks on post-quantum systems. So we will have 2 talks in this session, both on side channel assisted attacks on the post-quantum schemes. And so the first talk is given by Prasanna Ravi, and it will be about attacks on NTRU-KEMs.
Hello, everyone. Thank you for the introduction. So I'm Prasanna Ravi from Nanyang Technological University, Singapore. And this work was jointly done with Martinez Frederick Iseman, Shivam Basin, Anupam Chattopadhyay, and Sujoy Sinha Roy. So let's start with a bit of motivation. So I think it's fair to say that lattice-based schemes have dominated the NIST PQC process in the category of KEMs. And predominantly, there are 2 major categories of lattice-based KEMs. One's based on the learning with the error rounding problem, and the others based on the NTRU problem. And during the course of the NIST PQC process, lattice-based KEMs were heavily scrutinized by side channel attacks. And there were several categories of side channel attacks. And one of the most prominent categories of attacks was called as side channel assisted churn ciphertext attacks. And in this, the attacker's main idea is to craft malicious ciphertexts and query the decapsulation procedure. And the corresponding side channel leakage is used to actually realize an oracle, which provides incremental information about the secret key. And the attacker queries the decapsulation device with several such ciphertexts to actually recover the entire secret key. Now, why are these attacks interesting? Because these attacks have very nice features. So firstly, attacks are fairly generic because they exploit inherent algorithmic properties of the target scheme. And in most cases, they require minimal or almost no knowledge of the implementation, and hence can be readily ported. So the attack can be readily ported to both hardware and software. And through this talk, I'm also going to try to convince you that this is probably the easiest side channel attack that's possible on lattice-based KEMs. I might be wrong, it's debatable, but I'll try my best. So there are three different flavors of such attacks based on the type of oracle that you want to realize through side channels. So first is the plain text checking oracle based attack. The second one is the decryption failure oracle. And the third is the full decryption oracle. And if you look at the taxonomy of existing side channel assisted churn ciphertext attacks, you'll actually see that there are quite a few attacks on the LW and LWR based side, but there's probably none on the NTRU based schemes. So this begets the question if there are similar attacks that are possible on NTRU-based KEMs, and if so, are NTRU-based KEMs more easy or difficult to attack compared to LW and learning with the error and learning with the rounding based KEMs. So we answered these two questions positively in this work by proposing generic side channel assisted churn ciphertext attacks on NTRU-based KEMs. So we target both the finalist, both NTRU, which is the finalist, and the NTRU prime, which was the alternate finalist candidate. And we show that the attacker requires approximately the same effort to break both NTRU-based KEMs compared to KEMs based on the learning with the error and rounding problem. And our attack requires a few hundred to few thousand churn ciphertext queries for key recovery. And the attack works for all parameter sets of NTRU with an NTRU and NTRU prime with 100% success rate. And we experimentally validated our attack using EM side channel on the ARM Cortex M4 microcontroller. So in a nutshell, this is our contribution. So we try to level the playing field by proposing attacks on for NTRU-based KEMs as well. And let's start with a bit of background for NTRU-based KEMs. So as you all know, KEMs are cryptographic primitives that are used to derive a shared key between two untrusted parties. So you typically have three procedures: the key generation, encapsulation, and decapsulation. So here we have Alice running the key generation process to generate the public key and secret key. And you have Bob using the public key and an internally randomly generated message to generate a ciphertext and a shared session key K. And you have Alice who uses a ciphertext, decapsulates the ciphertext with the secret key to generate the same shared session key. Now, it turns out that Alice can actually reuse her public key and secret key pair multiple times to generate multiple session keys. And this is what we refer to as a static key setting. And our attacks are actually applicable in this particular setting. So Bob is our attacker who actually queries Alice with malicious ciphertexts for key recovery. And compromise of the secret key leads to recovery of all the session keys. So this is how decapsulation looks like. So we start with decrypting the ciphertext to recover the message. And then the message is fed into a re-encryption and a verification process, which basically validates whether the ciphertext was a validly crafted ciphertext or is an invalid ciphertext. And for a valid ciphertext, you generate a valid key, which is marked in green here. And the key is basically dependent on the message, public key, and the ciphertext. And if the ciphertext is invalid, then you basically generate a pseudo-random key, which is marked in red. And this works fairly correctly with a very high probability. And this framework is secure against churn ciphertext attacks. So how does a side channel based churn ciphertext attacks work? So basically the basic idea is that the attacker builds ciphertexts in order to control the value of a secret dependent variable, which we refer to as the anchor variable. And subsequently, the attacker uses side channels as an oracle to obtain some information about this anchor variable. And the attacker does this for several such ciphertexts, which ultimately results in key recovery. So in order to understand how this attack works for NTRU-based KEMs, we need to understand how NTRU-based encryption works, which lies at the core of NTRU-based KEMs. So we start with the key generation procedure, which involves sampling of two ternary polynomials, F and G. And as you all know, NTRU works with polynomials and polynomial rings. So we have two ternary polynomials, F and G, and then the NTRU instance is calculated as H equal to 3 times G times inverse of F, where the NTRU instance is the public key and the ternary polynomials F and G are the secret keys. In the encryption procedure, you have the ephemeral. So you sample another ternary polynomial R, you multiply it with the public key, and you generate H times R, and then you add it to the message, which is encoded as a ternary polynomial again, and you generate the ciphertext. And in the decryption, you multiply the ciphertext with the secret key polynomial F, and then you reduce it modulo 3 and multiply it with F inverse, which gives you the message. So I'm not going to go into the details of why this decryption works, but what's important to note is that there's this particular variable called A, whose absolute maximum value of the coefficient should not cross a certain threshold that's called Q by 2. And if it does, then it results in a decryption failure. But KEMs like NTRU and NTRU prime were designed in such a manner that this particular failure does not happen. So they're basically perfectly correct KEMs. So now that we have some background on NTRU-based KEMs, I'll jump into the first attack, which is a plain text taking oracle-based attack. So this attack is basically inspired from the classical chosen ciphertext attack on the original NTRU scheme by Yolme and Yu in Crypto 2000. And the attack works in two phases. So in the first phase, which is called the pre-processing phase, we search for a base ciphertext, and whose leakage actually reveals critical information about the secret key. And once you identify the base ciphertext, in the subsequent key recovery phase, you use the base ciphertext to build multiple attack ciphertexts whose leakage ultimately recovers the secret key. So this is the whole idea. And now let's start with the first pre-processing phase. So the attacker chooses a ciphertext of this fashion, which is K1 times T1 plus K2 times T2 times H, where T1 is X bar I1 plus X bar I2 and so on until IM with M terms, and T2 is X bar J1 plus X bar J2 until so on until X bar Jn with N terms, where I1, I2 until IM and J1, J2 until Jn are randomly chosen indices, and the constants K1 and K2 are basically multiples of 3. And now if you look at the corresponding intermediate variable A, you can actually see that A is nothing but 3K1 times T1 times F plus K2 times T2 times G. Now, what's important to note is these two products, T1 times F and T2 times G. So if you look at T1 times F, it's nothing but X bar I1 times F plus X bar I2 times F and so on. And in NTRU basically works in polynomial rings where multiplication of a polynomial with X bar I1 rotates the polynomial by I1 indices. So basically, the product T1 times F is nothing but rotation of F by I1 plus rotation of F by I2 and so on and so on. So T1 times F is nothing but the sum of rotations of F. And if you look at the absolute maximum value of a coefficient of T1 times F, it's nothing but M. So if you want to visualize this, here you have multiple rotations of F, and the maximum value of M is possible when any particular coefficient for all the sum rotations of F has a value of 1. So only then the absolute maximum value for the coefficient is actually attained. And this is what we refer to as a collision. Now, obviously, if you increase the number of terms M, then the probability of collision actually decreases. So now with this idea, if you look at the variable A, and if you want to compute the absolute maximum value of A, then it's nothing but 3K1 times M plus K2 times N, because T2 times G has N terms. So this is the absolute maximum value for a coefficient of A. And the absolute maximum value is possible when there is a collision at the corresponding index. So if there is a collision between rotations of F and rotations of G at the ith location, there you have a collision. So now what the attacker does is you can actually choose parameters M, N, K1 and K2 in such a way that when there is a collision, then that corresponding coefficient goes greater than Q by 2. And we also choose parameters to actually maximize the probability of a single collision. So this is a visualization of the coefficients of A. And if there is a collision at the ith coefficient, the corresponding coefficient goes beyond the threshold of Q by 2. And this is what we refer to as a wrap failure. And if a collision occurs, then this particular variable E actually has a non-zero value where with a single non-zero term. And if there is no collision, then the value of E is actually 0. So what an attacker essentially has done is that using the chosen ciphertext, he has restricted the value of E to just 2 values. It's either E with a single non-zero term or E with 0. So now how do you detect such collisions? The obvious answer is through side channels. So if you look at this particular operation here, you're either multiplying with a 0 E or you're multiplying with a non-zero E. And this is very easily distinguishable through side channels without relying on any leakage models and so on. So this is what we refer to as a side channel based plain text checking oracle, through which you are trying to distinguish whether E is actually 0 or non-zero. So how do we detect collisions? So we do this using a simple Welch t-tests. So basically you decapsulate, so you have two sets. So in the first set, you basically decapsulate a 0 ciphertext, which corresponds to E equal to 0. And let's say you get 10 repeated executions for C equal to 0. And in the second set, you build a chosen ciphertext, and then you decapsulate it repeatedly, and then you get the second set, and then you compute the Welch t-test. Now I'm going to meander off a little bit to explain the experimental setup. So we performed our attacks on optimized implementations of NTRU and NTRU-prime from the PKM4 library. And the target platform is the STM32F4 based on the ARM Cortex M4 processor. So if you compute the Welch t-test, you will observe two possibilities. So the first possibility is that you don't observe any leakage, which means that there is no collision. And if you observe several t-test peaks, then you know that there was a collision. So now what the attacker simply does is you select the features above a certain threshold as points of interest, and you build templates for both the classes, E equal to 0 and E not equal to 0. So now that we have the templates and we have identified a base ciphertext, we are good to go for the key recovery phase. So in the key recovery phase, the attacker actually constructs attack ciphertexts using the base ciphertext. And these ciphertexts are constructed in such a way that the value of E is restricted to only two possibilities, E equal to 0 and E not equal to 0. And the value of E actually depends on a single coefficient of F. And obviously, F is a ternary polynomial and F has three possibilities. So you can use the information about collision or no collision as a binary distinguisher for to actually distinguish every possible candidate of F. And obviously, we have side channel information, so you can use the side channel templates to classify whether there is a collision or whether there's a no collision. So here we have a visualization of our classification. So on the left-hand side, you actually see the template for class O, which is equal to 0, and you have a template for class X, which is E not equal to 0. And on the left-hand side, you see a trace corresponding to class O, and on the right-hand side, you see a trace corresponding to class X. So you can see that both the graphs are both the traces are very easily distinguishable for both the cases. And through our experiments, we also verified that the single trace classification works with a 100% success rate. So on to some results. So we validated our attack on all the parameters of NTRU, and the number of traces required is between 1,800 and 2,900. And if you compare this with the same attack on Kyber, it also requires approximately the same number of traces. And if you look at the attack on NTRU-prime, the number of traces are slightly higher because there are a few complications like a rounding of ciphertext and so on. So the number of traces is slightly higher compared to the attack on NTRU. Yeah, this is our these are our results for NTRU-prime. And obviously, you can see that at no point during the attack, the attacker requires any knowledge about the implementation. So the attack is fairly generic. So though the attack works really well on NTRU and NTRU-prime, we have a few observations, particularly on NTRU-prime. And what we observe is that this information about this anchor variable, which is secret dependent, actually does not propagate beyond decryption. So in order to, so what happens in NTRU-prime is that it has a special weight check weight check operation, which actually fails for all our attack ciphertexts. So for all the attack ciphertexts, the output of the message is the fixed invalid message. So in order to perform the attack, the attacker can only rely on leakage from the decryption procedure, while leakage from the re-encryption procedure and the comparison procedure is still cannot be used for key recovery. So the obvious question is whether we can widen the scope of our attack to also target the re-encryption procedure and the comparison procedure. This brings us to the second attack, which is the decryption failure oracle-based attack. And I'd like to just simply present the idea for the attack. So the key idea is that the attacker takes a valid ciphertext and then adds the attack ciphertext that you use for the plaintext checking oracle attack, and he builds a perturb ciphertext. So the attacker basically queries with perturb ciphertexts, and these ciphertexts either decrypt to either a valid message or an invalid message. So either have a decryption success or a decryption failure. And this information can actually be used by an attacker to actually exploit leakage from the re-encryption procedure to recover the secret key. And this is what we refer to as a side channel based decryption failure oracle. And some results for the decryption failure oracle-based attack. So we performed our attack on NTRU prime, and the attack actually requires slightly higher number of traces between 4,000 and 5,000, because you have possibilities of false collisions, false positive collisions, false negative collisions, multiple collisions, and so on. But an attacker can choose parameters in such a way so as to maximize the probability of a single collision. So if at all he identifies a false collision, false positive or a false negative collision, he just has to simply repeat the attack, because that can be easily detected. So that's why you have slightly higher number of traces for key recovery. And if you compare this with the same attack on Kyber, it requires approximately 5,000 to 8,000 traces. So the cost of doing the attack on both NTRU and LW or Kyber is more or less the same. So I am not touching upon full decryption oracle-based attack because of lack of time. So I'll directly jump to conclusion. So in this work, we've basically demonstrated generic side channel SHO ciphertext attacks on NTRU-based KEMs. We have demonstrated 3 types of attacks belonging to the plain text checking oracle-based category, decryption failure oracle, and full decryption oracle. And the take-home message of this talk is that breaking NTRU KEMs through such attacks is actually very similar to breaking LW and LWR-based KEMs. And we experimentally validated our attack on the ARM Cortex M4 microcontroller, and our attacks basically demonstrate the ease of attacking unprotected implementations for key recovery, as our attacks are implementation agnostic. And I hope I've convinced you that this is probably the easiest side channel attack that could be done on lattice-based KEMs. So the code package is available at this GitHub repository. And yeah, thank you very much for your attention.
Thank you, Prasanna, for the nice talk. Are there questions? I'll see in the chat. So I have some questions. What is the success probability of the side channel part of this attack? And also, what is the complexity of finding the base ciphertext? Because is there some trade-off there?
Yeah. So yeah. So these are results for NTRU prime, and you have two numbers here. One is T base, which is the number of traces that you require to find the base ciphertext first. So you have to go for multiple iterations. So you build different ciphertexts and you check if there is a collision. If there's no collision, you go back, you try with another ciphertext and so on. And so it requires a few iterations. But then if you compare it with the total number of traces, it's
okay.
Yeah. And also for the other question on side channel classification success.
Yeah.
So the number of points of interest range between few hundreds and few thousands, because you have several operations to actually target. So at least from our experiments, we did not observe any failure.
Okay.
Yeah.
Okay. So it's like a really simple side channel part.
Yeah,
okay.
Exactly.
And so I had another question, but other questions? So how do you fix the thresholds?
The threshold is a parameter of the experimental setup, actually.
Yeah.
So if you want to target a device, you'll have to perform attacks in the same device earlier. So it could, I mean, it basically varies from device to device, but then yeah.
Okay, so you just maximize it and until the attack works better.
Yeah,
and,
exactly.
Okay. And last question, did you analyze the combination of this attack with lattice reduction? Because NTRU can be solved with some lattice reduction.
So we were able to perform full key recovery, so we did not.
Okay.
Yeah, but
Yeah.
I think.
Okay, well, thank you, Prasanna.
Okay, thank you very much.
Well, the next talk will be given by Andreas Johansson, and so it's about an attack on McEliece implementation.
This one is yours.
Yes. If this here is timing, you have 17 minutes. When you're green, you're okay. When it's red, it's time for questions. And you should
Okay. Yes. Okay, thanks for the introduction. So this is the outline of this presentation. So a few years ago, NIST announced a competition to find new cryptographic schemes that are believed to be secure, even if sufficient large quantum computers are built. So this summer, NIST also announced that a lattice-based scheme had been selected for standardization, but they also announced that there will be an additional round with alternative candidates, and possibly some of these candidates will be standardized in the future. Classic McEliece is one of these alternative candidates. So, Classic McEliece is a key encapsulation mechanism that is intended to be used during the establishment of symmetric keys. So it is built on neither writer's dual version of the original McEliece, and the original McEliece. I'll just continue a bit. It's a code-based scheme that was proposed in 1978. And its security is considered to be well studied. So both the original and the classic McEliece make use of binary GOPA codes. And the security relies on the hardness of decoding random linear codes. So this is an overview of classic encryption and decryption and classic McEliece. So first we have a plain text of length n and Hamming weight t. To get the ciphertext, we multiply the plain text with a public key. Then we send the ciphertext over insecure channel to the receiver, where we use an error correcting algorithm to decode the ciphertext with a private key or secret key. So to set the security level in classic McEliece, we have 3 system parameters. So n will set the length of the plain text. T will set the Hamming weight of the plain text, and M will define the final field over which all computations are performed. So the secret key in a classic McEliece is a binary GOPA code. And this code is defined by a polynomial g of x of degree t and a support n that consists of n distinct elements. So the input to the key generation algorithm are 3 system parameters n, t, and m. So first we choose a random support, and then a random polynomial g of x. Then we use the polynomial and the support to construct a parity check matrix for the code. And this matrix is then transformed into a binary systematic form. And the transformed matrix is used as the public key. And as a secret key, we use this g of x and the support. So there are some relations between the 2 secret key parts that we can take advantage of during an attack. So first, if we know the support, then we can recover g of x by using the definition of a GOPA code. And also, we don't need to know the full support to carry out this. Second, if we know g of x, then we can use the support splitting algorithm to find the support. But this only works if n is equal to 2 to the power of m. So in case that we have that n is equal to 2 to the power of m, then we can sketch on the idea of a key recovery attack. So first, if we can get some partial information about the support, then we can use this information to recover g of x. And once we found g of x, we can recover the full secret support. And in the submission of classic McEliece, there is actually 1 parameter set that can be attacked in this way. And I'll get back to the case when n is smaller later. So to recover g of x, we make use of the definition of a GOPA code. So from this definition, we have that all code words, C, must fulfill this relation. Then we can construct a new polynomial, C of x. And then by the definition of the GOPA code, we can factor C of x to get G of x. And to be able to build this C of x, we only need to know the secret support at the index set of the code word. So we only need to have partial information about the secret support. So if we know G of x, then we can pick a random support and construct a new code, C0. Then from C0, we can derive a generator matrix, and we can also derive a generator matrix from the public key.
Then we can feed these two matrices as input to the support splitting algorithm, and the output will be an index permutation between the two codes. Then, since we know the support of C0, we can use this index permutation to recover the secret support. And the case that why this only works when n is equal to 2 to the power of m is that for smaller n, it's hard for us to guess which subset of elements are in the secret support. So in our work, we have attacked both the hardware and software implementation of a classic McEliece. So the hardware were synthesized with level 1 parameters and then implemented on a Xilinx RTX7 FPGA. The software implementation was compiled with level 1 parameters for a Cortex-M4 microcontroller. Both the hardware and the software were then integrated with a chip whisper, which is a framework for measuring side channel that can be used for measuring side channel leakage. So both the hardware and the software implementation make use of the same decryption algorithm. So the input to this algorithm is the ciphertext and the two secret key parts. So first, the two secret key parts are used to construct the double size parity check matrix, which is then used to construct the double size syndrome. This syndrome is thus fed to a Bellekamp-Massey algorithm, and the output is an error locator polynomial sigma of x. And to recover the plaintext, this error locator sigma is evaluated over all the support elements. And if the sigma evaluates a 0 for a particular support element, then we set this bit I to a 1, otherwise 0. So in our work, we have focused on the fifth step of the decryption. So one should note that we can control the shape of the sigma. So for example, if we encrypt, create a plaintext where only the three first bits are set to ones, encrypt this and send it for decryption, then this sigma will be of degree 3 with roots at the three first support elements. So both the hardware and software implementation make use of an additive FFT to speed up the evaluation of the error locator. So the evaluation is done in a deterministic way, and this sigma is evaluated over all the field elements. So no matter which element are in the secret support, for a fixed sigma, this FFT will run through the same steps. So the only input to this additive FFT is this error locator, which we can control by crafting ciphertext. So important thing here is that if for a fixed sigma, no matter which element are in the secret support, this FFT will run through the same intermediate values during the evaluation. And this is what we exploit during our attack. So the idea for our attack is that if we can create a plaintext where we only set bit I to a 1, then if we encrypt this, send it to the decryption, then the sigma will be of degree 1 with a root at the support element alpha I. Then depending on the system parameters, there are only 2 to the power of m possible degree 1 polynomials. And if we can distinguish between the evaluation of different polynomials, then we can predict the value of this alpha I. So if we can determine arbitrary support elements, then we can mount the partial key recovery attack. So here the goal is to create this polynomial C of x. And as I said before, we only need to know the support elements at the index set of this code word C. So to reduce the number of support elements that we need to determine, we would like to find a code word with low Hamming weight. So we can get valid code words from the generator matrix, which can be constructed from the public key. And from this matrix, it's quite easy to find a code word with a weight of r½ + 1, where r is equal to m times t. However, by using information set encoding, we can find a code word with even lower weight. And this in turn means that we don't need to determine so many alphas, which also means that we can reduce the time that we need to be physically close to the device under attack. For a full key recovery attack, there are 2 cases. So first, if n is equal to 2 to the power of m, then we use our partial key recovery attack to get d of x, and then we use the support splitting algorithm to get the support, and we're done. When n is smaller than 2 to the power of m, then we tweak our attack a bit. So now we try to find a matrix P such that when P is multiplied with a public key, we get the parity check matrix. So to be able to construct P, we need to know the M times T first elements in the secret support, as well as this G of X. So one way to reduce the number of support elements that we need to determine is to form the generator matrix, and then we just pick a random row. Since this we already need this M times T first element, we only need one additional support element to get G of X. So from our two attacks, we can see that the number of support elements that we need to determine depends on the system parameters. So this table is from classic McEliece submission, and it shows the system parameters for different security levels. So for the first four, we see that n is smaller than 2 to the power of m. So in this case, we need to recover the r+1 support elements. But for one of the level 5 parameter set, we see that n is equal to 2 to the power of m. So in this case, our partial key recovery attack is equivalent to a full key recovery attack. So here we use information set decoding to find a low weight code word. So in this table, we see that by running this algorithm for about 2 minutes, we can find the code word with a Hamming weight of 695, which is about 16% smaller than the random case. So we carry out our attack as a profiled side channel attack, which consists of a profiling phase and an attack phase. So during the profiling phase, we assume that we have access to a device that is similar to the one we later on intend to attack. But we have full control of this device and can set the secret key. We then craft multiple ciphertexts and send them to this profiling device. And then we measure the power consumption while it performs decryption. And then we use all of this measurement to construct a classifier that can predict some partial information about the secret key. So the attack phase is quite similar, but now we have a device that we can only set the ciphertext to. So, and we have no knowledge of the key, of course. So again, we craft multiple ciphertexts, send them to decryption, measure the power consumption. Then we take all the measurements or traces and feed them to our pre-trained classifier to predict some partial information about the key. So before constructing our classifier, we evaluate if it seems possible to exploit the leakage of this additive FFT. So for this, we collect multiple traces that corresponds to the evaluation of degree 1 polynomials. And then we split all the traces into 2 sets. So the first set corresponds to ciphertext to a specific ciphertext, which in turn generates a specific sigma as input to the FFT. And the other set corresponds to ciphertext that generates random sigmas of degree 1. Then we calculate the t-test between these 2 sets. For the hardware implementation, we can see that there seems to be some leakage present during this additive FFT step, which occurs in the second dark array region. For the software implementation, we can see even more pronounced leakage. So during the FFT, which occurs in the gray region. And the leakage detected towards the end occurs during the re-encryption, but we have not investigated this further in this work. So we use the chip whisper light to collect traces that we later can use to construct our classifier. So we use the following procedure. So first, we load a secret key to the profiling device. Then we pick a random I. And then we create the plaintext where only bit I is set to R1, encrypt the plaintext and send it to decryption. And then we measure the power consumption while the FFT step is executed. And afterwards, we label the trace with a support element alpha I. And then we repeat this procedure multiple times with multiple keys. So then we use machine learning to build a classifier. So the goal of this classifier is that it can predict this value of the degree 1 polynomial sigma. So if we can construct such a classifier, then during an attack, we can generate a plaintext where only bit I is set to a 1, send it to the target device, and then measure the power consumption, and then feed this as input to our classifier. So then we can predict the value of alpha I. So we make use of deep learning and a multi-layer perceptron model with only a hidden single layer. So for the hardware implementation, we use around 400,000 traces for training, and for software implementation, we use around 35,000 traces. So this is the result. We then evaluate our classifier on a set of new keys that were not used during training. So for the hardware implementation, we perform experiment on 30 random keys. And for each key, we can successfully recover the complete secret support. And each support element only requires one trace for prediction. So we have an accuracy of 100%. For the software implementation, we have similar result. So here we perform experiments on 90 random keys. And here we also get an accuracy of 100%. So one should note that if one use our partial or full key recovery attack, as I presented earlier, we actually don't need to recover the full secret support, but this result shows that our attacks can be carried out with a high success probability. So to conclude this presentation, we have presented, to our knowledge, the first key recovery side channel attack on both the hardware and software implementation of classic McEliece. And our attack exploits a leakage that occurs during the FFT step of the decryption. So for the level 1 parameter set, our partial key recovery attack requires 273 traces, and a full key recovery attack requires 796 traces. However, for one of the level 5 parameter sets, which is higher security, our partial key recovery attack requires 679 traces. And in this case, our partial key recovery attack is equivalent to a full key recovery attack. So for future research, we have some ideas of how we can improve our attack, such that fewer traces are needed during the attack phase. And also we are unaware of any protected implementation of classic McEliece. So we are interested in looking into how one could implement efficient countermeasures. Okay, thank you for listening.
Thank you, Andreas. Are there any questions in the room? In the chat? So I had several questions. I didn't really get the exact cost of the remaining key recovery, the cryptanalytic part. Is there possible trade-offs like trading some precision in the classification, so requiring less traces, and having a more costly key recovery phase? Do you think there are some trade-offs like that?
You mean trade-off between?
Well, work and number of traces.
I mean the pre-processing step.
No, the post-processing step, when you have at the end, when you from the information that you got, you recover the key.
Sorry.
What is the no worries. You had a slide with the attack without a side channel, just at the beginning when you presented the two techniques of attacks, when you have M, which is equal this one. So what is the complexity of this? I'm not the complexity of this this procedure.
I mean the attack complexity in number of traces.
No, in work. So I suppose that it's easy to get on a machine, like.
I'm not sure.
Okay, no worries. Okay, we can discuss it later. Other questions? Yeah, and so you said that. Oh, sorry. Yeah, maybe. Okay. You said that the FFT was the part that you attacked inside channel. Would you think that FFT would be like avoiding FFT would be a good countermeasure?
So So no, I don't think we should avoid this additive FFT because it will be a huge penalty in the efficiency.
Okay.
But maybe one should take a look at what happens before the FFT and maybe see if we can implement some countermeasures even earlier to disable this. So the key thing is that we can control this shape of the sigma. So if we can get rid of this, then this will actually, remove our attack.
Okay, thank you very much. No questions? Okay, so let's thank Andreas and Prasanna again. So one quick announcement. So there is the coffee break. So please take a cup of coffee and tea and go check out the posters. So the poster author did a very great job. And we invited the speakers from the last chess sessions that were online to present their paper as posters. So please go check them out.